All right. We're going to be working the 6.1 homework and going to be using the integration by parts formula, which is going to require that I fill out a table. That's the way I do it. And so we'll always have to be able to pick within our integral a choice for u and a choice for the dv, and then we'll differentiate down to get du, which will appear here. We'll integrate up to get v, that'll appear here, and then we'll try and redo the integral. So let me start with number one. Or sorry, what is this? Yeah, number one. And get integral x squared natural log x dx. Okay, so I need to first realize this is not any of the other techniques, so I don't see a basic substitution. But I do see that these two functions separated by multiplication, that if I take my natural log and I take the derivative of it, I get 1 over x. And then if I integrate this, I get 1/3 x cubed. And when I put those two together, so again, I'm trying to think ahead here. The derivative of this being 1 over x, the integral of this being 1/3 x cubed, that if I multiply these two together, that's just going to be a power of x, and that's a good thing. So I know my new integral is actually going to contain something I can handle. So I believe that'll be a good choice. So I'll start my table off. My u, I'm going to use natural log x. My dv is going to be the x squared and the dx. Everything else that was left up there. What the heck's going on over there? All right, derivative of u is, we said, derivative natural log of x is 1 over x dx. And then the antiderivative here of x squared is our v, which is 1/3 x cubed. And now I will rewrite using my formula. So this will be equal to ultraviolet, which are these two multiplied together, 1/3 x cubed natural log x minus a new integral, and then v du, which is going to be, hello, v, which is 1/3 x cubed, times du, which is 1 over x dx. And so now this becomes 1/3 x cubed natural log x minus, I'm going to bring the 1/3 out, integral, and then I have an x cubed divided by an x, so this is x squared dx. Y'all can talk. It's not, you don't have to be quiet.
I was watching the video that you posted.
Oh, shh, please. Keep it down. Keep it down, please. So the antiderivative of x squared is 1/3 x cubed. And then now I can do plus c. So negative 1/3 stays. Antiderivative of this is this, plus our constant, and this should be it. What were you saying? You were watching my video, what?
Well, nothing. Very interesting video. Very helpful.
Oh, good. Well, I wasn't sure if anyone was going to show up today, so I started making videos for the next section. So, but I'm open to help you out if you have questions. I'm just going to keep working through these if that's all right with you.
Yeah.
Okay. All right.
I have a question.
You ready? Yeah.
Here.
Yep. Yep. number 2. TE to the negative 3t. TE to the negative 3t dt. Y'all okay? Okay. All right. So again, we're going to have to do some sort of substitution. So which one of these gets better if I take the derivative? So derivative of t would just be 1. So that's actually going to get really nice in the new integral. The antiderivative of this, I should be able to handle. So let me try that as my choice here. U is t. dv is the entire thing that's left, e to the negative 3t dt. And then du is just 1 dt. And then the antiderivative going up here, you have to be a little careful because this is not just going to be e to the negative 3t. We're going to have a negative 1/3 e to the negative 3t. And that you can see if you do that on the side here. Just a separate problem here. Let u be equal to negative 3t. du would be negative 3 dt. You don't have a negative 3, so you have to scale it by negative 1/3 du dt. So what happens is you rewrite this integral e to the u times the 1/3, negative 1/3 du. And then that will turn into this. So, all right, so that's that. And now, this is equal to ultraviolet, so negative 1/3. That's this. I'm going to multiply the t. I'm going to put the t here. E to the negative 3t. Then minus, here's my new integral voodoo, which is going to be across here like this. So I'll have negative 1/3 e to the negative 3t dt. And I can pull the negative 1/3 out and make it a plus. Integral e, oh, forgot the third, 1/3 e to the negative 3t dt. We just did this integral, and so we know this what this one turns out to be, but we have a plus 1/3 in front. So negative 1/3 t e to the negative 3t plus 1/3 times antiderivative of this, negative 1/3 e to the negative 3t plus some constant. And then put these two together right there. We should be done. Minus 1/9 e to the negative 3t plus c. That's it. Anybody have a question?
The answer for 27 doesn't, it doesn't feel like it's going to derive correctly.
You mean like if you check it?
Yeah.
Let me see. Wait, the one you just did?
Yes.
That one?
Yes. The answer that I got, I don't feel like it's going to derive correctly.
You got secant squared?
I got
1/3 secant cubed
yes.
of x
Plus C.
plus c. So the derivative of this is chain rule. 3 comes out, it's gone. Secant squared x times, now derivative of secant, which is
Oh, okay, got it.
secant tangent x, and then derivative constant 0, and that's secant cubed.
And you can put this in.
Yeah,
Okay.
yeah. All right, x cosine 5x dx. All right, if we take derivative of x, it's going to get better. It's going to become a 1, and then we can find the antiderivative of this. So I think that's a good choice. U is x. dv is everything else that appears. Derivative down here is going to be du is dx. And integrating this, antiderivative of this is 1/5 sine 5x. And so this becomes ultraviolet. Those two multiply together. Minus integral voodoo, which is across like this. And so 1/5 sine 5x dx. I'll pull the 1/5 out. So this is equal to 1/5 x sine 5x minus 1/5 integral sine 5x dx. And then the last step is take the antiderivative of this. So 1/5 x sine 5x minus 1/5. And then antiderivative here, we have another 1/5. We have negative actually because the antiderivative of sine is cosine. 5x plus c. And then put it all together. So 1/5 x sine 5x plus 1/25 cosine 5x plus c. That's it. Questions?
It's a mouthful.
No, questions? Questions for you? No? Okay. This integration by parts is pretty much going to be kind of like the substitution. You just have to make that first step. If you make the first step correct, it all works out. But it's getting that first step that can be a trouble spot with these. Okay. For integral y e to the 0.2 y dy. Let's see what this text message was. All right, so for this one, this is very much like, oh crap, did I skip 2? Oh man, I did 5 instead of 3, oops. Okay. The one that I said was number 2 was actually number 5. So let me do this one. This is very much like number 5. It's rough. It feels like Monday squared right now. All right, so if I take the derivative of this, I get 1, or just dy, and then I should be able to integrate this pretty easily. So my choice of u here will be y. My dv will be everything else. The derivative of y is just dy, or 1 dy, and then the antiderivative here will give us v, and I have a constant in front of the y, so with the basic substitution we would get 1 over 0.2 e to the 0.2 y, and then 1 over 0.2 is actually 5, so this is just 5 e to, yeah, this is number 2. I messed up. Wait, no, this is 4, this is number 4.
Oh, no.
Okay, so ultraviolet minus voodoo. So this times this, so I'll put the 5 in front, then the y, and then e to the 0 or 0.2 y minus integral voodoo is this times this. So I'll go ahead and get the 5 out now, e to the 0.2 y dy. And we just integrated this just a second ago. We had to do that when we went from here to here, so we know it's going to pop this out. So I'm going to have another 5 that comes out with that. So our answer will be 5y e to the 0.2y minus the 5 times the 5, so 25 e to the 0.2y plus c. That's it. See if I can get back on track. So I'm going to do number 2 now because I accidentally did number 5. So number 2 is theta cosine theta du. D theta, sorry. D theta. So you ask yourself which one gets easier, which one gets nicer. So theta gets nicer, derivative of theta is 1, or just d theta, and then you can take the antiderivative of cosine. So u is theta, dv is cosine theta d theta, and du is d theta then, and v is sine theta. So this becomes ultraviolet theta times sine theta minus integral voodoo is diagonal, so sine theta d theta, and that antiderivative of sine is negative cosine. So you wind up getting a plus there because your negative comes out and hits the negative. So you're done. Question? No?
Question 26, but
Okay.
I might just need the unit circle. It's cosine pi over x over x squared times dx. So I was going to look for the unit circle. I don't know if I needed to use the unit circle for this one.
You need to look for something in its derivative. You need to figure out what you're going to use for substitution there. So do you see something in its derivative? All you're going to get off the unit circle is just values of cosine, which you don't need because you're looking for a function and its derivative sitting there in front of you, right?
So for you, maybe I use cosine?
The whole cosine, well, you have to use the whole thing. If you're going to use cosine, you got to take everything that's inside of it also.
So cosine pi over x?
Okay, so if you use that for u, what is its derivative? And then if you do it, its derivative needs to be there in the problem, right?
Yes.
So what's going to happen?
It becomes negative sine.
Okay, do you have negative sign?
I do not.
You do not. So probably not. That was you chose too much. Okay, you got too much because when you tried to take the derivative, it was right. So don't try and grab so much.
What if I use the pi over x?
Okay? That's the correct substitution. Now see if you can figure out why it's the correct substitution. You have to take derivative of pi over x.
Since the pi is a constant, it stays the same?
Stays out front, yeah, pi. You can look at that as being pi times 1 over x.
And then that becomes 1 over x squared.
Negative 1 over x.
Negative.
Yeah.
And we do have an x squared, so...
Just peel it all apart. Like rewrite it, peel the sign out front, and then put that x squared that's on the bottom right as a 1 over x squared on the outside. Okay, so for this one, I'm going to try and pick a u and then a dv. And these are in parentheses, so I can choose this whole thing to be my u. The derivative of this is just dx, which is nice. This one would be my dv, so I have to be able to integrate that, but I should be able to integrate that without any issues. So again, x minus 1 dv sine pi x dx. And so the derivative of this is just 1 or just dx, and then v we integrate negative 1 over pi cosine pi x. So this would require doing a little u substitution on the side, but I also showed you in class how to actually do this quickly. So it goes to that, and we should go straight to the formula now. So ultraviolet is the first one times this one. Make sure you leave that x minus 1 in parentheses. Times this. You know what? I'm going to redo that. I'm going to put the constant out front. negative 1 over pi is my constant, x minus 1, and then the cosine pi x. Okay, minus integral, I'm going to run out of room, so minus integral of this, negative 1 over pi cosine pi x dx. And the negative and negative become plus, so this equals negative 1 over pi x minus 1 cosine pi x. Negative negative is plus, 1 over pi, and now I need the antiderivative cosine pi x dx, which again I can do that. Antiderivative cosine is sine, but I have to take care of the pi x, so I have to scale by another pi. So negative 1 over pi x minus 1 cosine pi x plus, no more integral, okay, because I'm going to do it right here. I have a 1 over pi, but then I got another 1 over pi here, so 1 over pi times 1 over pi is 1 over pi squared, and then I have sine pi x plus c. So this is it right here. Number 7. Now we start getting a little interesting. Integral x squared plus 2x cosine x. All right. So now we have a little bit of an issue, because if we choose this to be our u, the derivative of it is 2x plus 2. So my new integral is going to have a 2x plus 2. Antiderivative of that I can handle, but that's not much better than this one was. Also, if I let this be u and I take derivative, I can get negative sine x, but then the antiderivative of this becomes something with x cubed in it, which I don't want in my new integral. So let's just see what happens. This is going to be one where I have to do integration by parts twice. So u is x squared plus 2x dv cosine x dx. So what I'm thinking is that, again, when I take the derivative here, I'm going to get 2x plus 2. The new integral is going to have a sign in it, and it's going to have the 2x plus 2. I'm going to repeat the process. I'm going to do integration by parts again in that new integral, and then I'll be able to reduce this one down one more time. So let's just see it happen. So du is going to be 2x plus 2 dx. V is going to be sine x. So this should be ultraviolet, x squared plus 2x sine x minus integral of voodoo. So it's this times this. And I do have a pretty ugly looking expression there. 2x plus 2 and then sine x dx. So this new integral is not that much better than this one, but notice that the power has come down. So I went from a quadratic expression to a linear expression. And if I do integration by parts one more time, I'm going to take the linear expression down to a number. So I will repeat integration by parts. Do you have a question? Or give me that look. Yeah? Okay, I'm almost done with this one. V is equal to negative cosine x. Derivative here is 2 dx. Okay, so now this is important that you get everything written down. What we're going to say is that this was our original ultraviolet minus voodoo, but this new voodoo had another integration by parts. So everything here is now going to require this integration by parts. So I'll write down the original answer, which was that. So this was my original ultraviolet minus, now here comes my new integration by parts, which is going to be this table, ultraviolet minus integral voodoo. So this times this, that negative's here, so be careful. Negative 2x plus 2 cosine x minus integral again, voodoo, the diagonal. And notice this voodoo I can do. So the negative and the 2 and cosine x dx. So negative 2 cosine x dx. And now on that one, I can do minus minus, that's plus, and then take the antiderivative. So I'm almost done here. So this was the first example, or the first homework problem that I've done where I had to do integration by parts twice. So x squared plus 2x sine x minus, now this minus and that minus become plus, plus 2x plus 2 cosine x. And then we said this, I'm not going to do the integral yet, but I have minus and minus, which come plus 2 out here, but then minus. So minus 2 integral, so I distribute that negative through here. And then I have cosine x dx. And the antiderivative of cosine x is sine x. So my last line and my final answer will be x squared plus 2x sine x plus 2x plus 2 cosine x minus 2 sine x plus c. And that is the antiderivative. Okay, what's up?
I understand how to do it. I used to
All right, this one's very similar to number 7 because you have quadratic.
Wear glasses.
And so if you do integration by parts one time, it's going to come down to a first degree. And if you do integration by parts again, it's going to come down again, and it's going to be a constant. And we can do antiderivatives of this all day long because it's just going to keep cycling back and forth between cosine and sine. So I'm already anticipating integration by parts twice. U is t squared. dv is sine beta t dt. Now du will be 2t dt, and v will be antiderivative of sine, which is negative 1 over beta cosine beta t. Always having to take care of that number in front of t. Remember, beta here is just a constant that we don't know. So we've got ultraviolet, so this times this, negative 1 over beta t squared cosine beta t minus integral voodoo, which is this way like this. And so we have a negative 2 over beta cosine beta t dt. I forgot my t. There we go. T. There it is. So that t right there. And I'll pull the negative 2 beta out. So negative 1 over beta t squared cosine beta t plus 2 over beta integral t cosine beta t dt. And I cannot do this integral. So I have to do integration by parts again. So I'll do that, I guess, in red. So just this part right here is a new integration by parts, a new table. This time, keep my u is going to be the linear or the linear expression in t, and then the dv will be the cosine because I can integrate that. And then du will be dt, and then v will be 1 over beta sine beta t. So derivative down, integral up, and now I'm going to rewrite everything in red using ultraviolet minus integral voodoo again. So here, right here, this is equal to negative 1 over beta t squared cosine beta t plus 2 over beta, and then here comes my new ultraviolet minus voodoo. So ultraviolet is this times this, so 1 over beta t sine beta t. Okay, and then minus integral of voodoo. So minus integral of voodoo is 1 over beta, and then sine beta t dt. And that's all in brackets. All right, so everything in this bracket is what I got from this, which was a new integration by parts, and I had a 2 over beta out in front. So what I'll need to do is actually now find the antiderivative of this, which should be pretty clean because there's no more t here. And then I'll distribute the beta through, 2 over beta through. Be done. So negative 1 over beta t squared cosine beta t plus 2 over beta. I guess I'll distribute this right here. I'll wait. Okay, 1 over beta t sine beta t. All right, I have a negative 1 over beta, but when I take the antiderivative of this, I get negative sine, or negative cosine, but then I also have that beta in here, so it'll be negative 1 over beta cosine beta t times negative 1 over beta cosine beta t. And then that's it. I'll have a plus constant. I'll put that at the very end. All right. Almost done. These problems are getting longer and longer and longer. So negative 1 over beta t squared cosine beta t distributing through plus 2 over beta squared t sine beta t distributing through. Negative negative is positive, plus so plus 2 over beta 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 cubed cosine beta t plus c. That's it. That's number 8. Hey, what's up?
What?
That's
Why are you asking?
I've always loved you.
what am I on?
Did you just say you
31
loved me?
Yeah.
What time is it? 10:40.
I do that. I do that.
Natural. Oh, this one's nice. Okay. Integral natural log of 2x plus 1 dx. All right, so I'm looking at this. Do I have a basic substitution? No. Do I have anything else? Now, you don't even think that integration by parts is going to work here either, because you really only have one factor. I mean, this is it. You don't really have two functions. But you can always look at this as being like a 1 dx. So let's try something here. I'm going to set up my integration by parts. I'm going to let u be that natural log thing. And that forces me to use the 1 dx as my dv. This may not seem like it's going to work, but it is. Du, the derivative of this, is 1 over it times the derivative of what's inside. So you should get 2 over 2x plus 1 dx. And then the antiderivative of this, well, the antiderivative of 1 with respect to x is just x. And so now we have ultraviolet, this times this, x natural log 2x plus 1 minus integral voodoo, which is this times this. So that becomes 2x over 2x plus 1 dx. And then how would we integrate that? So you can't split that up into two fractions, but I believe we can do a basic substitution here. Let's do this. Let's let u be equal to the whole bottom. And then the derivative of that is just the derivative of the top. The derivative of that is just 2 dx. Now we don't have a 2 dx, we have a 2x dx. So let me rewrite this integral and write it this way. X over 2x plus 1 times 2 dx. So I have a 2 dx right there. I have the 2x plus 1 right here. But I need to replace the x. So what I'll have to do is I'll have to take this equation. We've done this before in the previous homework assignment. And we would solve for x. So u minus 1 equals 2x. 1 half u minus 1 equals x. So solving that equation for x. Replace that x with this. So we have integral 1 half u minus 1 over, so that's just this, over this, which is u, and then this, which is just, where is it, du. I'm going to work backwards this way. Take the 1 half out, integral, this is u minus 1 over u, split that into two different fractions. U over u is 1, minus 1 over u, which is 1 over u, du. And now the antiderivative of each of these, I'm working backwards. Antiderivative of 1 is 1/2 u, because the variable is u. The antiderivative of 1 over u is natural log, so I have another 1/2 because I distribute that. Natural log absolute value of u. Now, what was u in this problem? It was 2x plus 1. So if I take this expression and I replace the u's with this, that's equivalent to this integral. So that'll be my next line. So my answer here was x natural log 2x plus 1 minus the antiderivative of this, which are these two pieces. So I'll put them in brackets. 1/2 u, 1/2 u, 2x plus 1, minus 1/2 natural log of u, which is natural log of 2x plus 1. All of that, plus some constant, and then I can distribute the negative through, which will change that to negative, and I'll change this to positive, and no more bracket. So that should be the final result. Yeah. That's it. I'll see you guys. Huh? Do you have a question about this?
For your examples right there,
Mm-hmm.
where did you get US?
Okay, so I took this right here, and I subtracted 1 on both sides, which gave me this. Well, because in... Well, yeah, that's the derivative right here. See, here's the problem. This integral, right, is what I'm trying to find this integral. Forget everything else. And there's really nothing easy you can do, but if you, this is a basic substitution. So this is what your homework was on last time. I'm going to let u be the bottom, right? Then du is 2 dx. But see, I have an x in here. I have 2 dx, but I have an x there also. So I need, if I rewrite this integral, bring the 2 dx to the back, I've got that. 2 dx is du. Over here, the 2x plus 1, I've got that. That's u. But x itself, I need to replace. So I take this equation, I solve it for x. So I move that over, divide by 2. That allows me to rewrite that top. Make sense?
Yeah, that makes
Okay.
sense.
Nice.
Okay. So
Looks like we'll see.
I'll see y'all, right?
Maybe. Yes.
In a couple hours.
House.
Is that supposed to be a sign?
No,
See you later.
All right, we'll see. Okay, I should be alone here now and maybe work through this a little quicker here. Ooh, yuck. Okay, we have number 10. Integral p natural log p dp. Wait, p to the 5th natural log p dp. All right, so this one is a little bit counterintuitive, I guess, because you might initially say, hey, look, I can pick p to the 5th because when I take its derivative, it becomes p to the 4th, 5p to the 4th, and I know I can do integration by parts again and get it down to p to the 3rd, and then p squared and p, and then eventually go away. So you know that repeating the integration by parts over and over, you should be able to reduce that power from 5 down to p, 5 down to a constant. Here's the issue, though. Taking this one, you'd have to integrate. And how do you integrate natural log p? That's a little more challenging. Differentiating natural log p is easy, though, because that's just 1 over p. And integrating this is relatively easy. So it looks like if we choose our u to be that natural log p and let dv be everything else, which is the p to the 5th dp, then du will be 1 over p dp, and the antiderivative here is 1/6 p to the 6th. And now look at our voodoo. Our voodoo, we have a p to the 6th, and then we have 1 over p. That's going to cancel one of the p's. We'll get p to the 5th, and that we can integrate. So this should be pretty clean. So ultraviolet, this times this, 1/6 p to the 6th natural log p. So I'm putting these in like a standard order. We like to put numbers in front, then powers of our variable next, and then any sort of weird function, trig function, log function, exponential function would come kind of towards the end. and then minus integral voodoo, which is this times this. So 1/6 p to the 6th times 1 over p dp. One of these p's cancel, it becomes a fifth power. The 1/6 is going to come out. So I have 1/6 p to the 6th natural log p minus 1/6 integral p to the 5th dp. The antiderivative of p to the 5th is 1/6 p to the 6th. So I'm going to get another 1/6 next to that one, which will give me 1/36. So minus 1/36 p to the 6 plus a constant. All right, number 11. Arctan of 4t. I'm going to write it this way. Arctan 4t dt. So this is like that problem we had, I think it was number 9, where it was just the natural log, and it didn't seem to be anything else we could work with. But in this one, this one appears to be the same thing. We only have one thing here. So you've got to choose something to be u. Never choose your differential to be u, because if you take derivative of the differential, you get almost like a second derivative, and we don't want to mess with that. So let's just try u being that whole arctangent thing. dv will be forced to be the dt. And now the derivative of arctan of something is 1 over 1 plus that something squared, 16t squared, times the derivative of what was in here, which is just 4. So I'm going to make that a 4 on top, dt. Now here we integrate up, and the antiderivative of dt is just t, because the derivative of t is dt. And so this should become ultraviolet, which is going to be t arctan 4t minus integral voodoo. So voodoo is this times this. That t comes and hits this, becomes a 4t on top. So integral 4t on top over 1 plus 16t squared dt. Now if you look at that, notice that that is a basic substitution. If I make a basic substitution here, okay, so this is a new integral. I'm kind of done with the integration by parts. A new integral, I'm going to let u be the bottom. The derivative of that is what 2 comes out, so 32t dt. I have a 4t dt, but not a 32. So if I divide both sides by 8, 32 divided by 8 is 4. 4t dt. So I tried to make this turn into a 4, so I had to divide by 8 on both sides. So I can replace the 4t dt with 1/8 du. I can replace the whole bottom with u. And so this new integral right here becomes integral 4d dt is 1/8 du. And then that's my 1/8 du, this part. So I'll still have like a 1 over this, which is u, 1 over u. And the antiderivative of 1 over u is natural log. So natural log u. And then that's equal to 1/8 natural log of u, but u is 1 plus 16t squared. So I know that this integral is going to become this. Just don't confuse the u here with the u there, because this was a different substitution. This right here was to get us the integration by parts formula, and then that was a new integral, so I could do any new substitution I wanted to. So my final answer is going to be this part here. So t arctangent, or times arctangent of 4t, and then I have minus this, minus 1/8 natural log 1 plus 16t squared plus some constant. And I'm done. Okay, I think that's a good point to stop this video. I'm going to come back and do a couple more. Okay, moving right along here. Number 12. Integral of arc sine x dx. All right, so this one is just like the one we did before. We don't have a whole lot of choices for our integration by parts table. So I'm going to go with u being the arc sine of x and then dv being dx. And remember from previous sections, the derivative of arc sine is 1 over the square root of 1 minus x squared. And that is actually formula on your derivatives reference page 5. It's formula number 19. So there's my derivative. And then v is the antiderivative of dx, which is just x. So we've got ultraviolet x sine, or arc sine x, minus integral voodoo, which is this times this. So that x I'm just going to put on the top. X over square root 1 minus x squared dx. And this is actually good because now I can use a basic substitution. I'm going to let u be equal to the whole thing underneath the radical. The derivative of that is negative 2x dx. I have an x dx, so I just scale this. Negative 1/2 du is equal to x dx. And now I just rewrite this. This integral now becomes integral. The x dx is the negative 1/2 du. So here it is, negative 1/2 du. And then I have, remember the x is already gone over here. I have 1 over this, so 1 over the square root of, but this whole thing is u. So this is the same as negative 1/2 integral u to the negative 1/2 du. And that's just square root of u is u to the 1/2, and then bring it up. And now we just use power rule. So I have negative 1/2, and then I'm going to leave a space. U to the, I add 1 to that, I get 1/2. 1 over 1/2 in front is a 2. And then I'll have a constant. But this is going to be just equal to, the 2's cancel, negative square root of u, which for me is negative square root of this, 1 minus x squared, square root of 1 minus x squared. So this whole integral becomes this. And so my final answer is going to be this piece here, x arc sine x, and then minus this, but there's 2 negatives there, so plus square root 1 minus x squared plus some constant. And that's it. All right, number 13. All right, 13 is a really important problem. Integral e to the 2 theta sine 3 theta. E to the 2 theta sine 3 theta d theta. So this problem is different than everything we've done up to this point. And this is definitely one of those problems that I like to give on tests because it's kind of a different technique for this. I mean, it's still integration by parts, but nothing's going to ever go away and become nice. And I did one like this in class. So let's see. If I choose my u to be this, we know the derivative of that is itself. And there's some constants there, but it's always going to be e to the 2 theta, e to the 2 theta, no matter how many times I do integration by parts. This one, if I use this as my u, then it's going to be sine and then cosine and sine and cosine. So there's no way to make that go away. So there's no easy way to make either one of them go away with integration by parts. However, what we're going to do is we're going to hope that when we do our integration by parts, we're going to get this integral to appear on the other side. And once we do, we'll bring it back to this side and we'll work out the answer. So let's see how this is going to go. I'm going to choose my u to be, I'm just going to let it be the e to the 2 theta. And that forces me to let my dv be everything else, sine 3 theta d theta. Now, derivative here, du, is going to be itself, but then times the derivative of what's up there. So 2e to the 2 theta d theta. The antiderivative here is negative 1/3 cosine theta. So right now we have that this is equal to ultraviolet, this times this, negative 1/3 e to the 2 theta cosine 3 theta minus integral voodoo, which is this times this. Now I'm going to try and do this in one step. I'm going to have a negative 1/3 times 2, so that's negative 2/3. I'm going to bring that out, and so that's going to make that a plus 2/3 integral, and then everything else, the cosine theta, and then the e to the 2 theta d theta. So e to the 2 theta cosine 3 theta d theta. Now this integral is still something I can't do. Nothing's really gotten better. I have a cosine here instead of a sine. So what I'm going to try and do is integration by parts again, so that when the next time I do it, I'm actually going to get this integral to appear on this side. So I'm going to make the same substitution I just made. And remember, I'm just working on this part right here. So u is going to be e to the 2 theta. The derivative of this is 2e to the 2 theta d theta. We did that already over there. dv is what was here, so cosine 3 theta d theta. And then the antiderivative is going to be 1/3 sine 3 theta. All right, so now I'm going to rewrite this. What I have is that, and because this problem is unique, I'm going to rewrite everything here. So I have integral e to the 2 theta sine 3 theta d theta is equal to this piece here, negative 1/3 e to the 2 theta cosine 3 theta plus 2/3 times, now my integration by parts, ultraviolet minus voodoo. This times this, so 1/3 e to the 2 theta sine of 3 theta, so there's ultraviolet, minus integral voodoo, so this times this. And again, I have the 1/3 times the 2, I'm going to bring that out as a 2/3, and then it's just going to be the e to the 2 theta, and then the sine 3 theta d theta, and then let's close my brackets. So look what I have. The integral I'm trying to figure out has actually appeared again exactly on the other side with some different constants. So what I'm going to do is first break this out of the brackets by distributing a 2/3 through. And then I'll write all of that up here. So I write this here, I write this here, and then I'll just continue right here so I don't have to rewrite the whole thing. This is all gone. Okay, let me see. Do this. So that's up to here, and then now distribute through. That's going to be 2/9, and then this expression, e to the 2 theta sine 3 theta, and then this times this, negative 4/9, and then this integral. Integral e to the 2 theta sine 3 theta d theta. All right, so that's what we get when we distribute through. Now what I'll do is I'm just going to use, properties of equations here to say that I can add or subtract anything from both sides. So I'm going to take this integral right here. Since it's minus 4/9, I'm going to add 4/9 of this integral, and I don't know what that integral is. I'm going to add it to this side, so they're going to cancel out completely. But what I do to that side, I have to do to this side. remember there's a 1 in front of that. So these canceled, right? These are gone. But over here, you have 1 of these plus 4/9 of these. So 1 plus 4/9 is what, 13/9? So we have 13/9 of this integral. Okay, equals -1/3 e to the 2 theta cosine 3 theta plus 2/9 e to the 2 theta sine 3 theta. And I'm going to try and get this integral by itself with a 1 in front of it. So I'm just going to multiply both sides by 9/13, just this flipped over. So if I multiply this side times 9/13, this becomes a 1. And I have to multiply this entire side by the same thing, 9/13. And that will distribute through to the constants like this. And so we should be at our final answer. So our final answer will be that one of these integrals is equal to, okay, we multiply here, 9/13 times this. So 9 times -1 gives me -9 over 13 times 3 is 39. And then I distribute the 9/13 here. 9 times 2 is 18. So this is going to become 18 over 9 times 13 is 90 plus 27. I can't do simple math right now. 90 plus 27. Why can't I do simple math right now? 117. All right, so 13 times 9. And then that piece. And then everything else is gone. And we are there. Let's just remember we need to add a constant of integration. We have isolated the integrand again, or the integral we wanted is here by itself, and we have it's equal to something, and that is the antiderivative. So what number was this? This was number 13. I'm actually going to look at the back. Oh, I don't have the answer, but I'll double check it in the solutions and see, make sure it worked out. So that's a good one. Okay, next one. Very similar problem. Number 14. Integral e to the negative theta cosine 2 theta d theta. All right. So here, we do the exact same thing we did on the other problem. Because I know if I take derivatives of e, it's never going to go away. And if I take derivative of cosine, it's going to keep switching back. So I'm never going to get it to vanish out. So let's go ahead and set up our table. U is equal to e to the negative theta. dv is everything that's still here, cosine 2 theta d theta. The derivative of u is negative e to the negative theta d theta. And that's because derivative of e to the negative theta is itself, but then derivative of negative theta is -1. Antiderivative here, okay, accounting for that 2 in there, we have 1/2 sine 2 theta. So we get ultraviolet. So this times that, 1/2 e to the negative theta sine 2 theta minus integral voodoo. So this times this, I have a negative, I have a half, I'm going to bring that out, but this is already a minus, so plus 1/2 integral, and now just the sine 2 theta and the e to the negative theta d theta. So I'm going to write that as e to the negative theta sine 2 theta d theta. So notice this integral here does not match this one, but it's close. So what I'll do is I'll do integration by parts again. Let me do it over here so I can have some space over there. So I'm doing integration by parts again. I'm doing it just on this piece right here. So I'm going to let u be the same thing it was here. U is equal to e to the negative theta. Du is equal to negative e to the negative theta d theta. This time my dv is going to be sine 2 theta d theta. And when I integrate, I get negative 1/2 cosine 2 theta. And so here's what I've got. This is equal to 1/2 e to the negative theta sine 2 theta plus 1/2, and now bracket, here's my new ultraviolet minus voodoo. Ultraviolet, this times this, so negative 1/2 e to the negative theta cosine 2 theta, then minus integral voodoo. But remember, when I do my minus here, look what happens here. Negative and negative is positive, but I'm subtracting it, and then I have the 1/2. So I'm going to bring that 1/2 out. And then I have e to the negative theta cosine 2 theta d theta. And I know I'm close to going off the board there. I think I fit that in. Okay. Oh, close my brackets. All right, so what I'll do now is notice that the integral I'm looking for right here is now appearing over here, but I need to release it from the bracket, so I need to distribute that 1/2 through. So I'll do that on the next line, and I'm actually going to cheat again. I'm going to just reuse what I have up here already. Okay. So this is this plus, oh, actually it's going to become a minus. So minus 1/4, and then e to the negative theta cosine 2 theta. And I've been using parentheses, so I'll use them again. And then 1/2 times that is going to be negative 1/4 integral e to the negative theta cosine 2 theta d theta. So I've released it from the brackets. And by doing that, I'm actually allowed now to move it to the other side. So I will add to both sides. Yes, I'll add 1/4 of this integral. Whatever it is, I don't know what it is yet. And they'll cancel over here. But if I do that over here, I have to add it over here. Add 1/4 integral e to the negative theta cosine 2 theta d theta. And so when I take one of these and I add 1/4, I have 5/4. So 5/4 of this integral e to the negative theta cosine 2 theta d theta will be equal to all of this. 1/2 e to the negative theta sine 2 theta minus 1/4 e to the negative theta cosine 2 theta. And then this canceled out. And remember, you're going to have a constant integration. You can put it in at the very end. I'm just going to put it here now. And then I'm going to get rid of the 5/4 here. I'm going to multiply by the reciprocal. So I'm multiply 4/5 here. And then this will become a 1. And I have to do 4/5 on this side. And I'll put 4/5 out here. It doesn't matter if I multiply c times 4/5 because it's still a constant. I don't know what it is. So I'll distribute through here now. So when I distribute 4/5 to here, I get 4/10. So again, I'm going to cheat. I'm going to just erase this. 4/10. Oh, 4/10 is 2/5. And then I distribute here to here. And when I do that, I get 4/20ths, but that's the same as 1/5. So minus 1/5. And I've distributed, so I don't need this anymore. And I have my constant of integration. So, oh, and this side becomes a 1, so it's just this. So that's it. This is your antiderivative right here. All of that. All right, number 15. About halfway through here. Okay, so number 15, integral x e to the 2x on top over, in parentheses, 1 plus 2x quantity squared. All right. So really on this one, you're trying to figure out what you can use. Well, if you're going to use integration by parts, what are you going to choose for u? What's du? Is it obvious? There's almost like 3 things here. It's like an x, then times this, so that you could choose one of those to be your u, but then you have divided by this. So you actually have 3 things. Forgot my dx. So it's not so obvious how to choose your u. Remember that whatever you choose for your u, the other part you need to be able to integrate. So you look at this for a while, and I don't know, if you had just this squared, like 1 over the 1 plus 2x squared dx, if you had that as an integral, we could integrate this using a basic substitution. So I know I can integrate that, which means I could choose this to be my u. Let's see what happens if we do that. So no promises that this is going to work. Let's see. I let my u be x e to the 2x. I let my dv be everything else, which was 1 over 1 plus 2x squared dx, because I know I can integrate that. Now let's check out this derivative, because this derivative is really going to be helping me determine whether or not I want to stick with this or not. So du is going to be product rule here. So derivative of the first one, 1 times the second, plus the derivative of the second one, which is itself, times the derivative of what's up here, which is 2, times the first one. So e to the 2x times the 2 times the x, and all of that dx. All of that dx. Huh. That looks really ugly. I don't know if I'm going to want to voodoo this thing, but let's see what this does. So when I integrate that, remember, this is what I'm doing. I can make a basic little substitution. U is the bottom. Du is 2 dx. I don't have a 2 dx, I have a 1 dx, so 1/2 du equals dx. So I can rewrite this integral as 1/2 and then 1 over u squared, 1 over u squared, which is u to the negative 2, and then the du. And then the antiderivative of this, we just add 1 to the power. This should be negative 1/2 u to the negative 1, which is really negative 1/2 times 1 over 1 plus 2x. So that's what I would get there. So let me throw that in here and see if I want to mess with that or not. Negative 1/2 times 1 over 1 plus 2x. And right now you look at that and you're like, oh my God. I mean, ultraviolet, fine, we write that down. But voodoo, do I really want to mess with that? That voodoo looks terrible. Until you realize that on this du, they both have e to the 2x in them. So factor out an e to the 2x. What you'd be left with is a 1 here, plus over here you have just 2x, and then dx. And check this out. This, when you multiply this times this 1 plus 2x and this 1 plus 2x will cancel. I mean, the only way you know this is actually try it. I mean, it's not obvious from up here that this is going to work. So let me write it all out. I've got equals ultraviolet, this times this. negative 1/2, because I like to put my constants first. Then all of this, x e to the 2x times this, 1 over 1 plus 2x, minus integral voodoo. So when I do my voodoo, it's going to be this times this. I'm going to write it all out. The negative 1/2 I'm going to pull out and make it a plus, because it's already minus here. So that's plus 1/2. So that 1/2's gone. Let me write all this down, and then I'll put this next to it. So e to the 2x, 1 plus 2x, times 1 over 1 plus 2x dx. So that's everything. That's voodoo written out. And this one cancel. Isn't that great? Once you get that, this integral becomes, let me see. So this is equal to negative 1/2. I'll write it like this. X e to the 2x over 1 plus 2x plus 1/2 integral of e to the 2x dx. And that is easy to integrate. So we get negative 1/2 x e to the 2x over, this is multiplication, 1 plus 2x plus, okay, antiderivative of this is going to give us 1/2 e to the 2x plus a constant. And so we put those together and we get 1/4. Now I'm going to clean this up because I don't like the way that looks. So I'm going to put just the negative up top. So negative x e to the 2x over, I'm going to distribute the 2 through. So 2 plus 4x. And then plus 1/4 e to the 2x plus c. There we go. And if you take the derivative of this, you should get that. Quite the mess, quite the mess. These are getting harder as we go. This was not obvious at all to use that. If you choose a different u on that problem, you may be here for a while. Or I should say, if you choose a different u and a dv, that could really hang you up. All right. T cubed e to the t dt. 16. T cubed e to the t dt. Is that right? This problem seems to be a little bit too easy. Well, let's see what happens. So I know that if I take derivatives of t cubed, keep doing it, it's going to get lower and lower powers of t. And then antiderivatives of e to the t is just itself. So it looks like I'm going to be doing integration by parts several times here. So in my first one, let u be equal to t cubed. dv is then e to the t dt. Du is 3t squared dt. And v is e to the t. So integrating. So this should be ultraviolet. T cubed e to the t minus 3 integral t squared e to the t dt. So all I did was voodoo here. I took the 3 here and I brought it out. I had the t squared e to the t dt. And now notice the power came down on this, so it very much looks like this. So I'll do another integration by parts. Just this piece right here, integration by parts on that. And I'll do my table over here. U is going to be equal to t squared. dv is e to the t dt. du is 2t dt. v is e to the t. So we have that this is equal to t cubed e to the t minus 3, and then in brackets, ultraviolet minus voodoo. T squared e to the t minus integral voodoo. Here times this, the 2 comes out, and then I have voodoo, t e to the t dt. And let me go ahead and distribute the -3 through so I can get those brackets out of there. T cubed e to the t minus 3t squared e to the t. So that was from here to here. Now here to here I get plus 6 integral t e to the t dt. And now I'm going to go one more time with integration by parts on this piece right here. And I'll do that table right here. U is equal to t. dv is e to the t dt. This should be my last one, because when I take the derivative of u, I just get dt. And then v here is e to the t. So everything is a repeat of what we've been doing, except the powers on t keep coming down. So this becomes t cubed e to the t minus 3t squared e to the t plus 6 bracket, now ultraviolet minus voodoo. Ultraviolet, we're going off this table right here. Let me get this one out of here so I don't accidentally look at it. So that one up there, we're doing t e to the t minus integral voodoo. Voodoo is just this right here. So it's just integral e to the t dt. And I'm done there. And that's it. I can integrate this. The antiderivative of this just e to the t. So we get as a final result t cubed e to the t minus 3t squared e to the t. Now distribute the 6 through, plus 6t e to the t. The antiderivative, okay, so this right here is e to the t, plus a constant. So I'll distribute the 6 through. I'll get negative 6 e to the t plus some constant. Just be aware that that 6 had to come through this bracket. And that's it. This is your antiderivative right there. You could factor out an e to the t if you want, but that's good enough. All right, 17. Okay, so this is the first one that has the definite integral, but we're not doing definite integrals in here. So in the problem in the homework assignment, it has numbers here, and I'm saying to ignore those for now. We've got x cosine pi x. dx. So this one, all I need to realize is that if I let this be u, the derivative of that is going to be a 1 or a dx. And I can find the antiderivative of that. So this one is actually kind of easier than the one we just did, because it's just a very basic one-time thing, one application of integration by parts, and we should be done. dv is cosine pi x dx. Derivative here is dx. Antiderivative here, negative 1 over pi sine, oh, not negative. I don't know why I did that. Antiderivative cosine is sine. So sine pi x. So this becomes ultraviolet 1 over pi x sine pi x minus integral voodoo, which is across like this. And I pull that 1 over pi out, and I have sine pi x dx. And then the antiderivative of sine pi x is negative cosine. But so we have equals 1 over pi x sine pi x. And then we have minus 1 over pi times, now again, antiderivative of sine is negative cosine, but I have to account for that pi. So negative 1 over pi cosine pi x plus c. So 1 over pi x sine pi x plus, because negative times negative, 1 over pi squared cosine pi x plus c. Okay, number 18. Integral x squared plus 1 e to the negative x dx. So on this one, again, it has numbers here, but we're not doing those right yet. So just find the antiderivative of this. I noticed that if I let this be u, first time I do integration by parts, it's going to come down to like a 2x. If I do integration by parts one more time, it's going to come down to a number. And so that's good. This one's just going to cycle back and forth. So 2 applications of integration by parts should work here. U is equal to x squared plus 1. Du is 2x dx. The dv was the only thing I really had left, which was this. Integrate up, just be careful with that negative sign, negative e to the negative x. And so this becomes ultraviolet, this times this. I'll bring the negative way out front. Minus integral voodoo. So let's see what happens here. I have another negative, and I have a 2, so it's going to come out as a plus 2 out of my integral. And then I'll still have the x, then e to the negative x dx. So I'll do integration by parts again on just that part, just the integral, right, not the 2. So u is equal to just the x, du is dx, that's what I wanted. My dv was e to the negative x dx. That means v is equal to negative e to the negative x. And so this becomes equal to negative x squared plus 1 e to the negative x plus 2 times in brackets ultraviolet minus voodoo, negative x e to the negative x, that's ultraviolet, this times this, minus integral voodoo. Let's see, do I have a negative here? Negative and positive, so negative will come out, turn it into a plus, and the only thing there is e to the negative x dx. And I'm going to distribute a 2 through, but the antiderivative of this, right, the antiderivative, we can just do this mentally. We've done it twice already, so negative e to the negative x, no more integral sign, we'll have a plus c. So our answer is negative x squared plus 1 e to the negative x. 2 goes through here, negative 2x e to the negative x. 2 goes to here, right? So negative 2 e to the negative x, and I need to erase that. E to the negative x, and then plus c. That's it. You could factor out an e to the negative x again if you want, but just leave it like that. Actually, it might work out pretty nice if you factor out an e to the negative x. Let's do that just to see it. If I factor out an e to the negative x, I'll be left with this right here, negative x squared plus 1. This right here, negative 2x. And this right here, negative 2. And then plus some constant. And this is just a quadratic e to the negative x. This is negative x squared. And then we have minus 1, but then minus 2, so minus 3. And then in the middle, negative 2x plus c. And then you can also factor a negative out of this if you wanted to, but that's good enough for now. All right, what is it? 19. I'm on 19. Let me get a little. Whoa. Okay. What am I on? 19? Man, we've done so many of these. These are so similar to what we've already done. All right, but I'm going to do it 19 integral. See, r cubed natural log r cubed natural log r dr. We're doing on time there, 40 minutes. All right, so we did one very, very similar to this. It was actually number 10. So we see the natural log r, we know derivative, that's 1 over r. We can integrate this. It'll just be a power of r, and then those two will go together, and they should become something very nice. So u is going to be equal to the natural log r. dv is going to be r cubed dr. Du is 1 over r dr. And then the antiderivative of this is 1/4 r to the 4th. So we have ultraviolet, 1/4 r to the 4th times natural log r minus integral voodoo, which is cross. Notice that 1/4 can come out. When you do r to the 4th and you divide by r, you get r cubed. So r cubed dr. Antiderivative of this is 1/4 r to the 4th, and we hit that 1/4 out here again. So we get 1/16 out there. R to the 4th plus c. So I did this one already, just integrated it. Power rule. That's it. Number 20. All right, again, it has numbers. We're going to ignore those. Natural log y over square root y dy. All right. Well, I know that if I take u to be the natural log of y, the derivative is 1 over y, which is a power of y. And I know that this is a power of y, so if I integrate this, I'll have another power of y. And so when I put them together, I should have some power of y. So let me try this. U is equal to natural log y. Du is equal to 1 over y dy. dv is equal to 1 over root y dy. Now be careful, because what that means, we need to integrate that. Hold on just a second. So this is going to be integral y to the negative 1/2 dy. So we use our rule, we add 1 to this, which is 1/2, 1 over 1/2 in the front, so that's 2. So this is going to be 2 y to the 1/2, 2 square roots of y. So that's what this is. I'm going to actually write it as v is equal to 2y to the 1/2. And now, what the heck was that? Now we can write our ultraviolet minus voodoo. So ultraviolet is this times this, so 2 this, okay, I'll write square root of y and then natural log y, that's this times this, and then minus integral, and notice I have a 2 here, so I'll pull that out. And then I have y to the 1/2 over y to the 1/2 over y, which is the same as 1 over y to the 1/2, which is y to the negative 1/2. So this is y to the negative 1/2 dy. So see, that's what I meant. We were going to have a power of y left. So there it is. And now we just integrate that. So this is equal to 2 square root of y, natural log y, minus 2 times, let me give myself a space here, y, let me see, I add 1 to that, I get 1/2, and I do 1 over 1/2, which is going to be 2, so another 2 there, plus some constant. So final, 2 square root of y, natural log y, minus 4 square root of y, plus c, and you could at this point factor out a square root of y and a 2 if you want. Okay, I'm going to stop this real quick, come back, I've done the first 20. Okay, I'm going to be picking up here, doing some more videos here for the integration by parts. And let me get this started here. Get my microphone fixed. Okay, I think I left off doing number 20. So we are going to do number 21. Which was integral t cosine hyperbolic t dt. And again, we're going to ignore the numbers up here. So the only real challenge here is that we have a hyperbolic cosine function, which is a little bit different than what we've seen before. But we still have a t, and then we know the derivative of this involves hyperbolic sine, and antiderivative involves hyperbolic sine. So we know that to get better, a better integral and integration by parts, we'll go ahead and use the t as our u. So u is going to be t, dv is everything else we see up here, which is the hyperbolic cosine function, dt. The derivative of u is just dt. The antiderivative of cosine hyperbolic t is the hyperbolic sine t. And now this will be equal to ultraviolet, so this times this. So t hyperbolic sine t minus integral of just these two multiplied, v du, which is hyperbolic sine t dt. And the antiderivative of hyperbolic sine t is going to be hyperbolic cosine t, but not negative. So just go back and look at your formulas for the derivatives of hyperbolic trig functions. So this is just going to become minus cosine, minus because of this, minus cosine hyperbolic t plus a constant. And that's it. Okay, let's look at the next one. Oh, this was number 21. Okay, so the next one is 22. Okay, arctan 1 over x dx. So 22. Arctan, I'm going to put this 1 over x dx. All right, well, not real happy with this because I only have one factor here. So this is one of those ones where we don't have a lot of choices for u other than this itself, and it doesn't look like things are going to be nice, but let's just try it to see what happens. So I'm going to let my u be the arctangent of 1 over x, and then dv by default has to be the dx. And I'll do this one first. The antiderivative of here of dx, the antiderivative is just x. Now this derivative is a little involved, so let's think through this. Du is the derivative of arctangent of something is 1 over 1 plus that something squared, 1 over x. Square the whole thing, so that squares the 1 and the x on the bottom. So it just becomes 1 over x squared. But then times the derivative of what's in here. And the derivative of what's in here, remember this is like x to the negative 1. So the derivative of that is negative 1 over x squared. And then times dx. So this doesn't look very nice, but when we do our voodoo, things are actually going to be pretty good. So let's write out the formula. It's ultraviolet, so x times that, x arctan of 1 over x minus integral voodoo. So I'm just going to write all of this out. This times x. I'll put the x first. X times 1 over 1 plus 1 over x squared times negative 1 over x squared times dx. Now let me clean this up here. First of all, I'm going to put the x on top. I'm going to take the negative out here and bring it out, so it's going to be plus integral. The x is on top. On the bottom, notice I have this, and then there's an x squared out here. I'm going to distribute the x squared through. So x squared times 1 is x squared. And then x squared times 1 over x squared, the x squareds cancel, and you just get plus 1 dx. And look how clean this integral looks. Now in the front, I still have x arctan 1 over x. But this integral I can do with the basic substitution. If I just let u be the denominator, the derivative of that, 2x dx, I have an x dx, so I'm only off by 2, so I have to scale this. And then at that point, or at this point, I can rewrite that integral. So this integral becomes, the x dx is 1/2 du, so this is going to be 1/2 integral du. And then the x dx is gone. I have a 1 over this, but that's u, so this is just 1 over u. And the antiderivative of this is natural log absolute value of u plus a constant. So u is this, I'll put that in here. So I'm ready to rewrite my answer. Had the original ultraviolet minus, oh actually it became a plus, so plus, and then this integral right here, we just said turns into 1/2 natural log absolute value of u, but u was x squared plus 1 plus c. And that should do it. All right, let's look at number 23. Okay, for 23, integral cosine inverse x dx. Again, this is one of those ones where you only really have one choice for u. It's that inverse cosine, and that forces your dv to be dx, which means v is x, integrating, and then differentiating. So du -1 over square root 1 minus x squared. I'm just going to double check that. That should, dx, that should be our derivative. I shouldn't have to look this up, but I just want to make sure. Yeah. Okay, so that is our derivative of our cosine. So, I'm sorry, of cosine, yeah, cosine inverse. So, this ultraviolet, x, arc cosine x, minus integral, and then voodoo, this times this. So I'm going to slide the x on top, up here, and then I'm going to put that -1 out front. The -1 is going to change it to a positive. I'll have the x, and then the denominator, square root 1 minus x squared dx. Again, this one I can do with the basic substitution, use 1 minus x squared. The derivative of that is -2x dx. Scale this, -1/2 du equals x dx. So I've got the x dx is this. This whole thing inside here is u. So this integral becomes -1/2 integral 1 over the square root of u du. And then this right here is -1/2 integral u to the -1/2 du. And then just do your power rule on this, add 1 and then 1 over that. And so you should get a -1/2 times 2u to the +1/2, and then plus a constant. But remember, u is this. So the 2's are going to cancel here, and we'll just get negative square root, because that's what that means, of u, which is 1 minus x squared. So this whole integral right here becomes this, and plus a c. So my answer should be, that plus is going to change to a minus because of this, minus square root 1 minus x squared plus c. All right, let's look at number 25. Oh, wait, that was, sorry, number 24. Let's see. Integral r cubed over square root of 4 plus r squared. 4 plus r squared, 4 plus r squared. All right, dr. All right, this one is tricky. So what are you going to choose? So maybe you look at a basic substitution right now. And the question, I guess, becomes, you know, are you going to treat this whole thing as u? Are you going to treat just the top as u? Are you going to treat 1 over the square root as u? Do you see anything that gets better? I mean, I know if I use this to be u, r cubed, then I can differentiate that and get r squared. But then I'd have to integrate everything else. So let me show you what I'm saying. If I do this, then dv will be everything else that's here. So the question becomes, can you integrate this? So can you integrate something like that? And it's not obvious. Now let's see, we'll check our formula sheet, because that does look kind of like something I've seen in a formula. Let's see if that's on your first 20 formulas or not. No, you don't have that on your formulas in the first 20 of them. Now, you have this, well, you know what? On this page here, if you look at formula 25, okay, formula 25, I'll just write it out up here. I'm going to lose my page. Formula 25 says if we have integral du over square root a squared plus u squared, that'll equal to natural log u plus square root a squared plus u squared plus a constant. That's formula 25. And so we have that, we have this right here. Here's the problem. Even though we can go from here to here with that formula, and we can go here down derivative easily, think about what voodoo is going to be. This new integral is going to be this answer right here times 3r squared. That's going to be a mess. It's going to be a disaster, because I'm not going to have any hope, I don't think, of integrating that very easily. So it doesn't appear that that gets any better. So we're kind of at a little bit of a standstill here, which is why this is one of the harder problems. So I'm going to try something a little different. Okay? If this were just an r up here, then this would be basic substitution, because I would have, here's u, the derivative that's right there. But it's r cubed. So watch what I'm going to do. I'm going to rewrite this r cubed as r squared times r. And let me try a basic substitution to start the problem. I'm going to let u, basic substitution, not integration by parts. I'm going to let u be equal to 4 plus r squared. Then the derivative of that, we know, is 2r dr, which I have an r dr here, right? I'm talking about just this. That I can scale both sides, 1/2 du is r dr. But I still have to resolve what is r squared then, because this right here is u. The r dr is going to be taken care of, but the r squared has to be taken care of. So this is where we can go up to this problem here, or that part of the equation, and we can solve for r squared. So r squared is equal to u minus 4, subtracting 4 on both sides. So let me see what happens here. I'm just going to do this basic substitution. This integral is going to become, the r squared is u minus 4. All right, and then over, this right here is square root of u. And then the r dr was 1/2 du, so I go 1/2 du. And now this is a pretty basic integral here. We actually did not even need integration by parts, because we can split this up into two integrals. So I can go 1/2 integral, let's see, u over u to the half is u to the half. And then minus 4 over u to the half is 4u to the negative 1/2 du. And that's just power rule on each one, so I take the antiderivative of each one. I'll continue up here. Actually, I'll see if I can squeeze it in right here. So this is equal to 1/2. Now, let's do the antiderivative. There will be a plus c out here. Antiderivative of this, add 1 to that, we get 3/2. 1 over 3/2 in the front becomes 2/3 u to the 3/2. And then here we're going to bring the negative 4 with us, but we add 1 to this, that gives us 1/2. 1 over 1/2 in the front is a 2. So that's going to become a minus 8 u to the 1/2. And now you just need to remember what was u. U is this. So, and I'll distribute this through. So let's see what we get here. Here to here, the 2's cancel, you get 1/3. U was 4 plus r squared to the 3/2. And then here to here is minus 4, then 4 plus r squared to the 1/2, plus a constant. And that's it. There was no integration by parts. I'm sure you can do it with some integration by parts, but this is clearly the easier way because you recognize that little pattern here, that you could peel that r off. Now, just for kicks, I'm going to check this. I'm going to take the derivative. Because I didn't use integration by parts, I'm going to take the derivative of my answer just to check it. And remember that what we should get at the end is this. So let's see. I'm going to take this here, chain rule, right? 3/2 comes out, I'm taking derivative, not antiderivative. 3/2 comes out, hits this, the 3's cancel. I have 1/2, 4 plus r squared. I subtract 1 from this power, so I get 1/2. And then I take times the derivative of what's inside. Derivative of what's inside is 2r. And I'm done with that. And then I'm going to subtract from that the derivative here. So subtract from that. Okay, 1/2 comes out, hits the 4, that becomes a 2. Then it's the 4 plus r squared. And I subtract 1 from that, so that's negative 1/2. And then times the derivative of what's inside, which is 2r. And I'm done with the derivative. Now let me clean it up because I want to show you, we want to verify that it's equal to that. So, wait a minute, 2, yeah. So this 2 and this 1/2 cancel. So this right here is just r square root, so there's r square root 4 plus r squared. Minus here 4r, and then this is a negative, so it's going to be on the bottom. Watch. Let me do it this way. 4r over square root 4 plus r squared. Now right now it doesn't look like we have that up there, but these are two fractions. Here's a fraction. And so I can get a common denominator. So that means I have to introduce on this fraction a square root of 4 plus r squared on the bottom and the top. So when I put it up here and down here, this times 1 will get the common denominator, but when I multiply this times this, the roots, these two roots go together and basically go away. So what you're left with is, let's see, the 4 plus r squared. That's what you get when you multiply this times this. And then you still had an r out there, minus 4r, then over the common denominator. The common denominator was this right here, so square root 4 plus r squared, which equals, now distribute this r through, 4r plus r cubed minus 4r over square root 4 plus r squared. These cancel, and you get r cubed over the square root of 4 plus r squared, which was the original problem. Nice when it works out, right? Okay, so let's see here. I only have about 20 more minutes, see how many more of these I can do. Number 25. Integral natural log of x, the entire quantity squared dx. Now, be careful here because that squared is acting on the entire natural log. It is not acting on the x only. If that squared was on the x only, then we could use the property that allows us to pull that out. But we can't because the squared is on the entire thing. So we cannot do that property. Well, so again, we're kind of like, well, what do we choose for u? I mean, I think the only thing we can choose would be maybe the whole thing. Let's try it, see what happens. And that forces dv to be dx. All right, so the derivative of this, we have to use chain rule. The 2 comes out. We have natural log x, all of that to the first power, which I'm not going to write, times the derivative of what's inside, which is 1 over x. Then dx. Right, derivative of natural log of x, 1 over x. Over here, we integrate, we get x. All right, so let's see what happens. We've got ultraviolet, x, natural log x squared minus integral this times this. So notice that this x and this 1 over x are going to cancel each other out. And all we're going to be left with is 2 natural log x dx. I'm going to pull the 2 out. 2 integral natural log x dx. Hold on, there's someone at this thing. Yes, sir.
Giovanni?
Yes, sir.
Hi,
Oh, are you? So now we need to try and integrate natural log of x, but we don't have a formula for that. So what we're going to do is just repeat the integration by parts. So we'll set up u is equal to natural log x, dv is dx. We'll integrate from here to get x. We'll differentiate here, du is 1 over x dx. And so this integral right here, right, everything I have in here, is going to be a brand new integration by parts. It'll be another ultraviolet minus voodoo, so let's rewrite what we first had from the first integration by parts. And then subtract from that 2, and then now in brackets, integration by parts here. So ultraviolet minus voodoo, integral. Now voodoo, look at this, is going to be nice, okay? Because look, you have x here, 1 over x here. They cancel, all you're left with is dx, or in other words, just 1 dx. And so that all you need to know is the antiderivative of 1. So this is going to be x, natural log x squared minus 2, x natural log x minus antiderivative of 1 is x, plus some constant of integration. And that's our answer. After we clean it up a little bit, we'll be done. So x natural log x squared minus distributing. So we get minus 2x ln x plus 2x plus c. And that's it. So I'll check this one again. It'll take about 2 more minutes. All right. Okay. So I'll integrate this one, or I'll differentiate this one just to check it. So it's going to be a little complicated. We have a product rule here. We have a product rule here. So product rule on this, I'm going to get derivative of x is 1 times this. And then derivative of this times this. So derivative of this, we did that earlier. It was 2 times natural log x times 1 over x, but then times this one times x. Then we have minus. Now we're doing product rule right here. Derivative of 2x is 2 times the natural log x plus, now be careful because that minus was out here, so if we do product rule here, leave the minus out, do the plus inside. Derivative of natural log x is 1 over x times the 2x. Finish the product rule there. Derivative here is pretty straightforward. 2, derivative constant 0. So hopefully, I'm hoping everything over there cancels and all I'm left is with this. So these are gone, which gives me natural log x squared, and then 2 natural logs of x And then here we've got minus, distributing the negative minus 2 natural logs of x, and then distribute here to here. These x's cancel. I get minus 2 plus 2. Gone, 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 gone. And this is the integrand. That's what we were hoping for. Okay, that's going to be it. I'll try and do the others some other time. 25. So I need to do 26. So I think there's 1, 2, 3, 4, 5 more to go. Okay, I'm going to try and do a couple of these problems here real quick. 6.1. I think I finished up 25, so I was on number 26. So number 26, integral e to the s sine t minus s. E to the s sine t minus s ds. So the variable in the problem here is s, and we're going to treat t as if it's a constant. I'm noticing that I've got a product here. I've got, if I choose this to be u, I know that derivative's it's just going to stay itself. If I choose this to be u, I know it's going to switch back and forth between sine and cosine. But this was the one that we had seen where we get that special thing to happen where we get this to appear again somewhere, and then we move it to the other side. So let's go ahead and start. I'm going to let u be equal to e to the s. Du is e to the s ds. V is sine t minus s ds. And integrating up, we get, dv. V is equal to negative, hold on. You have to be a little careful here because we have a negative 1 in front of the s. So remember, we're going to have to scale by the number in front of s. So we're going to have to scale by negative 1, or 1 over negative 1. But the antiderivative of sine is negative cosine, so the negative and the negative will cancel and become positive. I shouldn't say cancel, but so it'll be this. So take derivative real quick. Derivative cosine of something is negative sine of it, right? Act like there's a negative out here. Then derivative of the inside, derivative of t is 0. Derivative of negative s is negative 1. That negative 1 comes out over here, and that's why you have a positive. So that's correct. So this equals, right down here, this here equals ultraviolet, e to the s, cosine t minus s, minus integral voodoo here, here. I'll just rearrange it, e to the s, cosine t minus s ds. And now I'm going to do integration by parts again on this piece. So I'm going to set up a new table. And I'm going to let u be equal to e to the s again. And du will be e to the s ds. dv will be the cosine of t minus s ds. And then v this time will be negative sine of t minus s. Because the antiderivative of cosine is sine, but then we have to scale by the number in front of s, which is negative 1. So we had to put a 1 over negative 1 here, which is the same as negative 1. All right, so what's here is going to be a new ultraviolet minus voodoo. So we have the original ultraviolet right here, minus, in brackets, this new ultraviolet, which is this times this. So negative e to the s sine t minus s minus integral voodoo, which is here and here. And notice I have a negative sign here, so I'm going to make this a plus. And then we're going to have e to the s sine t minus s ds. Let me make sure that it's coming out. Oh, okay. Close it off. And now what I'll do is, I see that this integral is the one I originally wanted. So all of that is equal to this. Let me distribute the negative through. When I do that, I will get this, e to the s cosine t minus s, minus minus is plus, e to the s sine t minus s, and then minus and plus is going to be minus this integral right here, e to the s, I'm running out of room, sine t minus s ds. And now I'm going to add this integral to both sides because it's the same integral. So I add it to both sides. When I add this integral, whatever, goes away. When I add that integral over here, I get two of them, right? So I'm going to put that down here. I'm going to have two of these integrals. Is equal to this, these two right here. E to the s cosine t minus s plus e to the s sine t minus s. And then I just divide both sides by 2. So the 2 goes away here. I'll just put a 1/2 in front of this. I'll squeeze a 1/2 back in here. And then remember we have a constant of integration. Okay, so that's 26. 27, I believe I did 27 in class. But on 27, they're telling you to make a substitution first. Oh no, I didn't do this one. So it says, first make a substitution, then use integration by parts. So integral cosine square root x dx. So the substitution I'm going to make is, it doesn't look like I should make this, I'm doing basic substitution. Doesn't look like I should make this substitution because I don't see the derivative of this anywhere. But let's see what happens. I can say du is 1 over 2 root x dx. And remember in class I also said that you could square both sides instead and then take the derivative here implicitly. So the derivative of u squared is 2u du equals derivative of x, which is just dx. So you could use this instead of doing this. See, on this side, what you have to do is you have to get your dx by itself to match up here. So you have to multiply both sides by 2 root x, and that would give you this. And then you have to realize that u is the square root of x. So this will become 2u du, and that's what we have right here. So this is a little cleaner. So now I'm going to rewrite the problem. I have cosine, square root of x is u, and then dx is 2u du. So I'm going to put the 2 out here. I think I'll put the u in front of the cosine. 2u, so 2u du. And now for this one, I notice that if I use integration by parts, I can choose this as my u, even though I can't use u because I already used it. And I know that when I transfer the derivative of this is going to be 1, and I can integrate this pretty easily. So now integration by parts, I'll do it here. I can't use u, so I'm going to use w. I'll still use dv here. dv has to be the cosine u du. W is u. dw is du. v is sine u. So integrating up. So this integral becomes 2, don't forget the 2 on the outside, then ultraviolet minus voodoo. Ultraviolet minus integral voodoo, integral sine u du. And I should be able to do that. Antiderivative sine, I can figure that out. So now we have 2, I'm going to distribute the 2 through, 2u sine u. And then the antiderivative of sine of u is negative cosine u. So the negative is going to become a plus here, and the 2 is going to come through. So 2 cosine u plus a constant of integration. And finally, let's replace all our u's with what u was in the problem, which was x. So 2 root x sine root x plus 2 cosine root x plus c. So that's 27. I have probably enough time for 1 or 2 more. 28. t cubed e to the negative t squared. All right, so on this one, again, it's telling us to make a substitution first. This is almost a basic substitution because the derivative of t cubed is 3t squared, and I have a t squared up here, but the problem is we can never have the derivative. In basic substitution, we can never have the derivative appearing somewhere else, like hidden or trapped inside of another function. So we can't do it that way. But we know that the derivative of this is going to be negative 2t, and I actually do have a single factor of t here. I have 3 factors, but there is actually 1 factor in there too also. So let's try that. Basic substitution, let's let negative t squared be u. du would be negative 2t dt. And so let me rewrite this so we can see that we actually had that. That's t squared e to the negative t squared times t dt. So I just peeled one of the t's off over here, and so that I could get this t dt to match up. And so that means I'm going to scale this. Negative 1/2 du will be equal to t dt. So I'm going to replace t dt with this. And I'm going to replace, let's see, negative t squared with u. And then the question is, what do I replace t squared with? We'll just take this equation real quick, multiply both sides by negative 1. We know t squared is just negative u. So this integral becomes t squared, which is negative u, times e to the, that's just u, and then times t dt, which is negative 1/2 du. And I can pull the negative 1/2 out. The negative here becomes plus. So we have 1/2 u e to the u du. And now for this, notice integration by parts. If I choose this to be my u, right, the derivative of that will be 1, and then integrating that will be easy. So we should be able to set up a table here for integration by parts. But the basic substitution got us to this. So here we go. Can't use u, so I'm going to use w again. I'm going to let w be the u. That means dv is going to be the e to the u du. That means v is e to the u. dw is du. So this integral I'm going to rewrite up here. This integral becomes, let's see, 1/2, then integration by parts, ultraviolet, u e to the u, minus integral here, e to the u du. Antiderivative of e to the u is itself. Let's distribute the 1/2 through. So 1/2 u e to the u minus 1/2 e to the u, again because the antiderivative of this is itself, plus c. And now let's just replace all of our u's with what u was. And I already erased it, but it was negative t squared. So this is going to be negative t squared. I'll pull it out the negative. Negative 1/2 t squared e to the negative t squared. And then minus 1/2 e to the negative t squared plus a constant. So that should be it right there. All right. Let's see if I can get one more in. I'm sorry. I know it seems like I'm rushing, but I am, because I'm in a hurry to get to class here. 29. Integral. We have theta cubed cosine theta squared d theta. We're supposed to make a basic substitution first. So I'm going to make a basic substitution. Noticing again that the theta squared, the derivative of that is just 2 theta. I have 3 factors of theta here. So I already know ahead of time I'm probably going to need to peel one of those factors of theta off. Here it is right there. But let's make our substitution. U is going to be theta squared. Du is 2 theta d theta, which means 1/2 du is theta d theta. So that theta d theta right here is going to be 1/2 du. So now this integral becomes theta squared, which is u, cosine theta squared, but that's u, times 1/2 du, so I'm putting du back here, 1/2 out here. And now again, we're kind of getting into repetitious mode here. I can do integration by parts on this. If I differentiate that, it goes to 1. If I integrate that, it becomes sine. So our table, using w to be u, dv is cosine u du, dw is du, v is sine u. And now this becomes 1/2 ultraviolet u sine u minus integral of sine u du. Antiderivative of sine is negative cosine, so that's going to become a plus when I integrate, and I'll distribute through, so I'll have 1/2 u sine u. Again, that becomes a plus because the antiderivative of this is negative cosine. I have a 1/2 cosine u plus c. Replace all of your u's with theta squared, and we're done. So we should get a final answer of 1/2 theta squared sine theta squared plus 1/2 cosine theta squared plus c. One more? Yeah, let me see if I can get 30. If I get 30, I'll be happy. 30. So for 30, we're integrating, oh, I did this in class. I did this in my class lecture. So I'm not sure I should even work through this. Maybe I'll just get it set up. U is equal to root x, basic substitution. I'm going to square both sides. I'm going to differentiate both sides. We just did this just a second ago. And then I'm going to notice I can replace dx with this. I can replace square root of x with that. So this integral becomes integral e to the u. But then dx is 2u du. So here's 2, here's u, here's du. And we've done that already. So you do another integration by parts table here and break that down the rest of the way. Okay, I think that's it. That's all I'm going to do for this section. The other problems in this section that involve reduction formulas, watch my lecture video. Those are more involved. I would probably only give that as a bonus question to try and come up with a reduction formula. So I won't do a video on it. All right, I hope that all helps for this section. Have a good one.